Hello, AP Stats. This is Chapter 6, Random Variables, Section 6.1. We're just going to go through the first section today, and some of this is definitions, so make sure you get it down in your notes that you should have printed out, and you clearly understand. This goes along with your reading. Just you should make sure you're looking through and reading through your first section of the book as well. A variable is a quantity whose value changes. We know that. We have two kinds of variables we've talked about before, discrete and continuous. Discrete variable, make sure you write it in, as a variable whose value is obtained by counting. Here's some examples: numbers of students present in class, number of red marbles in a jar, number of heads when flipping 3 coins, student's grade level. All of these are countable things, and so your answers would be 1, 2, 3, 4, and so forth. A continuous variable, on the other hand, is usually found by measurement, such as height, weight, time it takes to get to school, distance traveled between classes, and it's continuous because, of course, you'll be getting fractions between these things, and these amounts are always rounded. So think of one more example and write it in of what might be a continuous variable. Now, a random variable is a numerical value that describes the outcome of some chance process. So, for instance, know that it has to have numerical value. So if you're talking about a chance process such as flipping a coin, the random variable would not be heads or tails. The variable would be a number, as for instance, if you're flipping the coin 10 times, how many heads are you going to get? So you might define X to be the amount of heads you have gotten after flipping a coin 10 times. So make sure you're looking for numerical variables. They will always be capital letters. So when you start out your problem, you're going to say capital X or capital Z or whatever is going to equal this random variable and define it. One thing that makes it a lot easier is writing it out in a probability distribution. And a probability distribution of a random variable gives all the possible values. So for instance, if you're talking about the number of heads and 10 flips, you could have 1 head, you could have 2 heads, you could have 3 heads, and so forth through 10. So you'd have to list every one of those and the probability of each one of those situations. A probability distribution can be discrete or continuous. It must include all possible values of the random variable. Probability of each possible value of X. Individually, these must be probabilities, so they're numbers between 0 and 1 inclusive, and the total probability, of course, must add up to 1. Here's an example. This is the example from your book. You're tossing a coin 3 times, and there we've written out the sample space. And notice we have defined X. That's our random variable. So always start out by defining your random variable. X equals the number of heads obtained in 3 flips. So if we write out when X is 0, the only way we can get no heads is tails, tails, tails. If X is 1, and there's 3 different ways we could get 1 head. If X is 2, 3 different ways, and if X is 3. So here's what a probability distribution looks like. And here you'll often just want to write these out on your own just to help you figure out probability problems. Sometimes you will be asked to fill these in. Possible values of X are 0, 1, 2, and 3. And there are their probabilities. There are 8 possible situation events in the sample space, and out of the 8, one out of the 8 gave you 0 heads, and so forth. Notice this all adds up to 1. And you can graph these in a probability histogram. Now, a histogram is how you're always going to graph a probability histogram, discrete random variables. And often these bars will not be touching because when they are discrete like this, but in this case they are. And here you can see kind of what it looks like, all the different possibilities. Here's another one. We've talked about this one before, where X is sum of 2 dice. And gosh, this is used so many times, and I told you there's kind of 2 ways, the pyramid way and the chart where you where you write down all the possible sums, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 on each column and row, and you look at how many times you can get each possibility. And notice there's always a possibility of 36. 6 times 6 is how many different sums, ways you could get the different sums. Here are a list of possible x values. Sums are 2, 3, 4, and so forth. And so there's your probabilities, and they again add up 1. And so here's our probability distribution and histogram. Notice again, these bars are not touching. Usually the histogram they do touch. Since they're discrete, like I said, sometimes you'll see them not touching and a little more like a bar graph, even though it's not, just because you can't get like 2.5 or 2.9. That's why they don't touch. You'll see it either way. Continuous random variables. We've already worked in Chapter 2 a good bit with continuous random variables using normal curves. That's the most popular way to use them. Discrete random variables commonly arise from situations that involve counting something. Situations that involve measuring something are continuous random variables. Know that they will not come out in a histogram, but a density curve. We've already spent a lot of time on density curves. The ones we've seen the most, of course, are bell-looking curves, like normal curves. Density curves don't even have to be curves. They just have to be of the x-axis, and the area under them is the probability of the event, and that has to total up to 1. Continuous random variable y has infinitely many possible values. All continuous probability models assign probability of 0 to every individual outcome. So the probability of y equaling 1, for instance, will be 0. So you're always looking at the range, the probability of y being between 1 and 5, for instance, just like we did with normal curves. So here's an example. This is the example from your book, page 351, about heights of young women. And notice we always start by defining the variable. Capital Y is the height of randomly chosen young woman. Y is a continuous random variable whose probability distribution is, don't forget that normal notation, means it's normally distributed with a mean of 64 and a standard deviation of 2.7. What is the probability that a randomly chosen young woman has a height between 68 and 70 inches? Totally review here. Just make sure when you're doing a probability with a normal curve, you graph it first, draw the normal curve, somewhere show the mean and the standard deviation are, and you could do this either way you wanted to in normal notation, or just write it on the curve. Show where your probabilities are and shade it. If we wrote this out, we could do this on our calculator just with norm CDF. Low number 68, high number 70, the mean is 64, standard deviation is 2.7. Very easy. No, though, a lot of times on multiple choice and stuff, you will see them first changing these to z-scores. 68 is the slower value, minus the mean of the standard deviation, gives you a z-score of 1.48. 70, the higher value, minus the mean over the standard deviation, gives you a z-score of 2.2. And if you use norm CDF with z-scores, you don't have to put in mean and standard deviation. You just put in the low z-score and the high z-score. So either way you do this problem, both of these are going to give you the same answer, which is 0.052. That's the area under that curve right there in that shaded region, and it's the probability. So in context, always put your answer in context. There's a 5.6% chance that a randomly chosen young woman has a height between 68 and 70 inches. Okay, we're going to stop right there, and we will be right back.